All right, good morning, everyone. Let's get started. So let's do a brief review of what we covered last time. So in the previous lecture, we started off saying we're going to review some of the changes that were introduced in ChatGPT OSS model, released open source from OpenAI. And there were some implementation details regarding SWGLU and multi-head attention. And we also talked about LoRa, which might be extremely useful for you if you plan on fine-tuning a base model that you download from Hugging Face for your project. So if you compare 20 versus 120 billion model, the major difference is in number of experts in MOE, which is the per token matrix multiply after attention. And that's what we're going to cover today. So last time we talked about this interweaved gate and linear for SWGLU, where after you get your input X, you do fused matrix multiply, and every even dimension and odd dimension become gate and linear respectively, and you apply SNU to the gate to element-wise multiply with linear, and you do clipping, only the upper bound clipping for gate, and lower and upper bound clipping for linear. That was the difference. And we talked about sharing the key and value caches, key and value heads. So, for example, here there is 2-to-1 sharing. So every two query head shares the same key and value head. And here, if you take it to the extreme, every single query head shares a single key and value head for primary efficiency. And also talked about LoRa, where the idea is very simple. You don't want to, actually you cannot really fine tune all the model weights because there are so many weights, and you don't have access to the GPU farm. So what can you do? You need to somehow reduce number of parameters to influence. And the way to do this is to introduce a low rank matrix A and B, where this intermediate dimension R, it's much, much less than the input and output dimension of a matrix. And matrix B is initialized to all zeros. So if you do a forward pass on W prime, initially at least, there's going to be no difference. And when you do a backward, you only backpropagate on the manageable parameters, which are A and B. And there's a stock gradient on W, so you don't backprop here. That was pretty much it, and it was extremely primary efficient. So if you do apply LoRa and use low rank matrices, you only influence about 0.2 to 0.7% of the total weights. All right, so let's open up the next lecture. So we're going to continue from the previous lecture and talk about the different implementations that was introduced in OSS model, namely MOE and sliding window tension. So the running theme is all these things that we're going to cover. The main concern is efficiency. How do we efficiently scale the number of parameters so we are primary efficient? Meaning, given the fixed number of parameters, we want to pack as much information as possible during training. And for fine-tuning, we only want to change the weights for the subset of the weights so that we can do it more efficiently. Okay. So we've introduced MOE in the lecture before. So the basic idea is your input. So okay, before that, if you look at a transformer block, the first thing happens is the attention, where you have, if you have input token length of L, you compute L squared number of the attention score, and you also have the residual connection, and then blah blah blah, and per each token representation, you're going to do matrix multiply. And that's the MLP layer that we are talking about. And here, they're going to use MOE. So we're going to have lots and lots of MLP in parallel. And we're only going to activate a subset, a selective subset of the MLP weights through this implementation of router. So we're going to have sparse activation of which MLP layers to activate. And then, given that we're going to take the weighted averaging of the selected ones and compute the matrix multiplies with the selected matrices. And this is for the weighted combination with the router weights. That was the basic idea. So what's the advantage? We only activate very subset of the MOE layers or weights. So when you do forward inference, you don't have to do matrix multiply with everything. And that's where you get the computational advantage. So I already explained this part, but just to look at it more concretely, let's define some notations. K is number of activated experts. N is number of total experts. So K is a lot less than N. And what I mean by expert is a single matrix multiply. X is your representation of a single token. It may be, it's basically whatever you get after attention. It's some representation or feature of a token, which attended to all the previous tokens. It's upsize some dimension. And EI is ith expert network. And we're only going to activate K experts and apply phi4 on the selected ones. And there's a router network here, which takes X and outputs R to the N. And it's computed by multiplying this router weight with your input token representation. And remember, this applies for each tokens independently. So there is no communication among different tokens here in this stage. And this is just for indexing. E of J is jth largest entry of the router output with arbitrary tie breaking. And how do we get the probability of the weights or the mixing weights? We only look at the top K activated router weights and turn it into probability by computing softmax. So you exponentiate the top K scores predicted by the router and normalize it. So we have this probability vector where it's of size n, but it's going to be k sparse. So among the k weights, they're going to sum to 1. And to compute the output, we're going to take the weighted averaging of the output of k activated matrix multiplies. All right. So here's a simple example. There are 3 experts, and we're only going to activate 2 of them, and the dimension is 2. So your 2-dimensional input token representation comes in. You multiply with this gate weight or router weight, and you have this 3-dimensional object. And we're only going to take the top 2. So the selected experts are the first and second one. And they're going to have, since the score is the same here, the probability mass for the first 2 experts is going to be half. Rest of them is going to be 0. And for the output, we're going to evaluate the first and second MLP weights and take the weighted averaging according to the probability. All right? So let's put this into the GPT-OSS context. It uses 2-layer MLP for each expert, and uses sweet glue between 2 linear projections, and K is 4. So each token is going to activate 4 experts. And for example, for 120 billion model, it has 128 experts, and 20 billion model has 32 experts. So 120 billion model, for example, has 117 billion total parameters, but per token, only 5 billion is going to be activated because let's compare the ratio. So out of 128, only 4 of them is going to be activated. All right? So we already discussed the details in the list about sweet glue last time. So if you have batch size, sequence length, 2 times intermediate dimension input, you have batch size, sequence length, the dimension output. And it's still a token-wise operation. And we haven't discussed what this EI is specifically yet. So this EI is you take your token, take the ith selected expert network, and this is the exact form. You take your token representation, matrix multiply with the first linear layer in the ith selected expert as a bias, apply SWI GLU, apply the second linear layer in the ith expert, and add the second bias. That's what this EI is. So for each selected expert, you're going to compute this operation and take weighted averaging according to the K weights predicted by the gate network or router network. So what are the parameters of each ith expert network? Weight and bias. There are 2 linear projections. So there are 4 objects inside each expert. And this gate and linear, as we saw in the previous lecture, is going to be implemented by one fused operation, followed by even and odd column split, and the clipping as usual. Here, we're going to introduce Einstein summation notation operation in PyTorch. If you don't know some operation in PyTorch, just look it up in PyTorch documentation. So it's very self-explanatory. So let's just read this first. So sometimes in the previous lectures, we had to do some crazy operations like reshaping followed by transposing and blah, blah. It was very complicated and not very fun, to be honest. And in OSS implementation, they use what's called Einstein summation, and it avoids this confusing transpose, squeezing, reshaping, all these things by explicitly stating the dimension labels. So what's nice about it is the performance. It's much more efficient than using loops or other ways. So it sometimes exceeds the optimized BLAS implementation. So GPUs naturally support efficient computation for Einstein summation. So to start off with an example, so let's say you have the first projector, MLP1, weight and bias, and you select the selected K expert indices, and this is going to be upsize, batch size, times sequence length, top K, because we've selected expert indices here, dimension, 2 times intermediate dimension, and your input X comes in, and this notation, BK, comma, BECK, arrow, BEC, that means these are 2 inputs separated by comma. So BK is your token. It's going to be upsize B times K. And your second input is going to be upsize B times E times K times C. And after the arrow, this is the dimension for the output. Okay, so the first thing is going to be batch size times sequence length, and second thing was top K. And this K is going to commute and disappear. They're going to take inner product across K dimension, and it's going to disappear. And the output shape is going to be B times E times C. So what is the kth dimension? That's the this dimension here. Right? It's going to take the token upsize batch size times sequence length, comma dimension to matrix multiply with this guy. So we're going to skip this complicated step where we need to transpose and matrix multiply and to blah blah blah. We're going to use this notation instead. So I suggest you read through this documentation as well. So it's comma separated for each operand, and output subscripts can be defined using the arrow in the string. So for example, if you have ij, one tensor of size ij, the other tensor of size jk, and output ki, it's gonna do automatic transposing of the output. Because without the transpose, if you do matrix multiply here, it's gonna be of size I times k. But here you defined it to be ki, so it's going to automatically take care of transposing the output. All right? All right, so, okay, let's just see one more example. So without the comma, it's going to instantiate a 4x4 matrix and have I. So it takes summation along one dimension. Which dimension? I don't know. You look it up yourself. Here, I comma j, ij. So x is of dimension I, y is of dimension j, and if you do I comma j arrow ij, it's going to take the outer product. And okay, let's see just one more example. So you have one tensor AS of size b times I times j. Tensor BS is b times j times k, arrow bik. So it's going to commute with dimension j, get rid of it, and the output is going to be of size b times I times k. All right? Sounds magical, right? All right, so let's continue. Okay, so we have provided for you the implementation for RMS norm and implementation for SWI-glue. It takes the output of the fused matrix multiply, splits it even and odd dimension, and does clipping and blah blah blah. And this is the MOE feedforward class that you're going to implement partially. So takes as input the dimension, input and output dimension, intermediate dimension, number of experts to activate. Number of experts to instantiate, and top K is the sparse activation. And the router is just a simple linear layer projecting from dimension to number of experts. And this is your MLP weights, number of experts times dimension times intermediate dimension times 2. Forward implementation is going to implement what we discussed above. So in the beginning, you have some dimensions. And here, you're going to take your input token representation X, reshape it such that only the dimension remains. So the rest of them, we're going to fold it into one dimension. So it's of size, batch size, times sequence length. We're going to compute the RMS norm and compute the router logits and select the top K experts and apply softmax. So we get the probability distribution on the weights for the K selected MLP weights. And this is the indices out of N corresponding to active K experts for this token. And we have provided a reference implementation for the first MLP. So here, the first dimension is number of experts. We're going to only select the K activated experts. We're going to keep the rest dimensions as is. So it's batch size times sequence length. Top K dimension 2 times intermediate dimension. So here, for the first matrix multiply, we're going to take the flattened X norm, which is of size, batch size times sequence length times dimension, and apply the selected first MLP weights and add the bias. And this is the corresponding Einstein summation notation. This is 2-dimensional, right? So we're going to call this B and K. And we're going to take the MLP weight, B times E for top K, times K, the dimension, times 2 times intermediate dimension. and output is going to be size BEC. First dimension remains as is, and second dimension is going to be top K, and we're going to commute the kth dimension, which is this guy. It's going to, after we commute and take the inner product, it's going to be gone, and the final dimension is going to be C, which is upsize 2 times intermediate dimension. Okay, so here is your to-do. Remember, EI is SWE glue of applying the first weights and second weight. And what else? And then you need to, after you compute SWE glue, you need to multiply with the second weight, this guy, and add the bias. And once you do that, you need to take the weighted averaging of the gating probabilities. And where is the gating probability? Expert visuals, expert weights. Yeah, we have already computed the expert weights. This is the P of X here in the notation here. Pi of X. That corresponds to this variable, expert weights. And then also there's residual connection and reshaping. All right, so let's take some time to implement this. And if you're unsure about its function signature and what it does, just Google search torch.einsum, and you're going to land in this page. And if you read it through, then you'll understand what it means. I think there was a question in the Kakao chat room about why different party heads will learn different weights or something like this. Here is my take, my opinion. So this is answer for more general question. So why does it do the right thing kind of question. I didn't look at the question carefully, but just to address it in a more broad way, here's my take. So what we're doing is optimization. So we define some laws and we optimize, and we always take the leap of faith that it will learn something globally optimum, which is not always true. Not always true. But it's a good way to think about it. So if it's globally optimum, then it's not advantageous for the query weight matrix or any weight matrix in general to learn redundant representation. It's advantageous given the fixed number of parameters to absorb as much information as possible from data set in such a way that it reduces the loss as minimally as possible. Okay, so how do you decrease the loss as minimally as possible in a way that generalizes? So that's always the framework in my head. And it's more primary efficient and I guess optimal to avoid learning redundant representation or redundant weight matrices. So because if you learn exactly the same weights for a couple of attention heads, or sorry, query heads, then it's going to be waste of the weights. So assuming you have plenty of data, So I guess another assumption is you have more data than there are weights. So there is more knowledge to be obtained from the data than there are number of parameters. So in that case, you want to push all the information to the weights as much as possible. So you're going to be losing information per weight, if you think about it. If you end up pushing the same data to a subset of the parameters. So if there's a redundancy, you're losing your information. So you have so much information, so information divided, some quantitative measure of the information divided by number of parameters, that's why you want to increase as much as possible. And sort of like pigeonhole principle, you don't want to have two pigeons in the same bucket, right? You want to spread as much information as possible in the weights. That's sort of the running concept in my head. And there were some theoretical papers like 5 years ago, I think. And people were wondering why neural networks work so well in practice, even though they don't find globally optimal solutions. Because, so we're solving, in terms of optimization, we're not solving convex optimization problems, so there's no guarantee of optimality. So we end up converging to local optimum, and but it works well on data sets. So there were some theoretical works saying all local optimum are equally as good as global optimum if you let it run for a significant amount of iterations. So about 15 years ago in ML research, people really disparaged works that doesn't have guarantee of global optimality. So people really didn't take it seriously if they don't show global optimum. But what these guys found out was obsessing over global optimality is useless. Converging to local optimum of much difficult problem ends up being much, much better. All right, anyways, how many of you have finished? Oh, wow, a lot of it. That's nice. Okay. So, all right, so we have already given the imputation for the first linear weight. So to compute EI of X, apply SWI-GLU and apply second weight matrix. Okay, so given Z, we're simply going to call our implementation here, which is already given. That's the output. And for the second weights, we're going to select the respective activated expert indices, and the output here is batch size times sequence length times top K, intermediate dimension. So for these three dimensions, let's call it BEK. And the second weights, it's going to be upsize batch size times sequence length, top K, and intermediate dimension, and dimension. Okay, so the first three dimensions match except the last one. And we want to commute in the shared dimension, which is intermediate dimension, get rid of it, and output is going to be batch size times sequence length, top K, and dimension. Okay. Okay, third, we're going to take the weighted summation of output of EIs according to the gate weights, gate probability distributions. And I'm going to skip the details. And then you add in this original input, X flat, for digital connection, and reshape the output so we break the batch size and the sequence length. Okay, so everybody finished copying? Okay, so let's check the dimensions. So as expected, so input shape is some batch size and sequence length and dimension, and output shape, output of the MOE that we just created is same as before. And there are 8 experts and 4 activations. So this is as expected, right? So you have something that's outputted from attention by matrix multiplying attention score without, with the value cache, value cache, and per each token representation independently, you're going to compute MOE, and input and output dimensions are the same. And inside the 2 matrices, in the intermediate step, the dimension gets blown up by a factor of 2, but gets down projected back into the input dimension. All right, so the second thing that's introduced in recent models is sliding window attention. Previously, we had this vanilla attention. So the tokens can attend to itself and all the past tokens to produce an output. And this tokens that comes after, we have, in our implementation, we have negative infinity weights for these masks, so that during inference we prevent the model from referring to the future. In sliding window attention, the tokens can reference itself and all the past tokens only up to the size of the window. So we restrict looking so long in the past. But the nice thing is if you stack the sliding window attention transformer blocks on top of each other, even though the first blocks, say in this figure, have field of view of 4 past tokens, the next block is going to have the field of view of the 4 tokens, but this guy has seen the past 4 tokens. So here, effectively, you have seen 8 tokens, even though your window size is restricted to 4. So it propagates so that this token all the way in the back has seen all the tokens. Make sense? And of course, to guarantee all tokens have access to all the previous tokens, you need to design the window size with the number of blocks, transformer blocks, carefully, so that your field of view of the last token has access to significantly long view of the past. All right, so that's the idea. You want to restrict how much into the past you can reference. So in the figure, the window size is equal to 3. And why are we doing this? Again, it's for efficiency. So in the attention, we had this quadratic cost, right? We have to take the outer product of the query and value for all the past tokens, and it's quite expensive. So in the vanilla case, we have complexity of t squared. And for the KB cache, we have to store key and value feature for every single token in the past. So the space complexity is linear in number of tokens. In the sliding window case, when we compute the attention score, the complexity is T times W, because each token can reference up to W number of tokens. And how about the space complexity? We only need to hold in the memory W recent token representations. We don't need to store all the KB values for whatever is out of the window. So W is going to be constant. This doesn't change normally, so it's constant. So we have O of T and O of 1 respectively. So what the OSS model does in practice is it does sliding window attention with window size of 128, but only to the even number of layers. Odd layers, they use full causal attention. But still, there's a significant number of savage in terms of KB cache. All right, so this is what we had before for causal mask. So this creates an upper triangular part of a matrix. So if you initialize some random matrix of size 3 by 3, push it to triangular upper or tri-U function, it's going to give you the upper triangular part. And this controls if you want the upper diagonal or lower diagonal components. So you will need to control this number in your implementation. And same thing, lower triangular function is same. So here. So it creates a lower triangular part of a matrix. And if you create a 3 by 3 matrix called tri-L, it's going to give you this lower triangular component. Same thing, you can control the diagonal to control if you want the upper triangular or lower triangular, if you want to control how much component you want to retrieve based off of the diagonal. So if you want to control, retrieve ones above diagonal as well, that's where you set this number. If you set this to negative number, it's going to set the diagonals to 0 as well. So this is going to be useful for your implementation. Upper triangular, lower triangular component. It's obvious, right? So if you have look at this figure, this 0 is supposed to be negative infinity in our implementation. So we already have given you this implementation for this guy, right? You only need to add in this component. So for that, you need to use this function. You just need to be careful with the diagonal function input. So this is already given. So you first create a matrix of ones, and other than that, it's going to be 0. And here, masked field is if the matrix entry is equal to 1, you set it equal to negative infinity. All right? And diagonal of 1 means 1's above diagonal. So anyways, this is what existed before. So we've been using this again and again so far. It's just a reminder. And this is what we're going to implement, sliding window mask. So it says here, position I can attend to positions max of 0, comma, I minus window size plus 1. Max of 0 so that we don't reference, we don't get out of bounds here. If you here, yeah, for example here, if you take window size, you reference out of bounds. All right, so there are two parameters, sequence length and window size, and should return the mask. So we're going to initialize with upper triangular matrix with negative ones, negative infinities. And here, okay, so what is this function? I'm curious. Duplicate. Torch.full creates a tensor of size filled with fill value. Okay. What if fill value is not provided? Okay, field value is negative infinity. So it's going to this is going to create a matrix of size sequence length by sequence length, all filled with negative infinity. And here we're going to select the upper triangular matrix of that negative infinity matrix, and for the lower triangular component, it's going to be initialized to 0. And once above diagonal, the upper triangular component is going to be set to negative infinity. Okay, so this is, I guess, another way to execute this function. So pictorially, it's going to, this line is to give you this orange part here, and you just need to add in this component here. And I think this function will be useful. How many finished? Okay. Right, so we're going to try to add in this lower orange part with filled with negative infinity. So we're going to have to create a lower triangular matrix where this part is negative infinity, rest of them is 0, so we can add what we create with what exists before. So we're going to call lower triangular matrix function. First, we're going to create a matrix all filled with negative infinity, and we're going to tweak the diagonal parameter so it's negative window size. Right? If you put a negative number in diagonal parameter, you get that number of entries below the diagonal, right? Okay, so other than that, rest of them that is not the lower diagonal matrix is going to be initialized to 0. So if you add this guy with this guy, then we have this figure. Once again, in our implementation, this orange is supposed to be negative infinity, and this is supposed to be 0. Sorry. Yeah, this is 0. Otherwise, it's negative infinity. I think it's better to change the figure. So we'll update it. So we'll create a new figure. It's confusing. Okay, so let's look at the shapes of different attention masks. So this is the full causal mask. You can only address what's before or yourself. This white component is negative infinity. You are prohibited from accessing the white component here. For sliding window attention window size 4, 8, respectively, you can only access the tokens for that many sliding window number of previous tokens in itself. So in summary, we talked about various things. We talked about Swiglu implementation with fused matrix multiply, clipping large values, and we talked about multi-head attention, grouped query attention for space savings and efficiency. Talked about LoRa for fine-tuning, which is going to be, I think, useful for your project. And talked about MOE. I think MOE is another way to increase what I just said about amount of quantitative information stored per weight, and sliding window attention for even more efficiency. And these are tricks that's introduced in the OSS implementation that's open sourced recently. Okay, so is lecture 13 available on ETL? All right, cool. Let me close all this window. So this is going to be the final lecture for the hands-on LLM part of the lecture series. But I don't think we're going to have time to finish this today. Let's do as much as possible. So in this lecture, the aim is to get you really ready to do your projects. So we're going to cover basics for PyTorch, in case you need to do PyTorch operations or build or make some modifications to the models. And Hugging Face is basically a web store where people upload available models. You can download it. You can use their APIs to fine-tune. So most of what we covered in the lecture is going to be already be available through APIs. So I think LoRa, you don't need to implement anything. You just do .LoRa or something like this. There's APIs for MOE, LoRa, everything. So in terms of project, you're gonna download the model from Hugging Face and do some PyTorch. That's pretty much it. Okay, and I'm still thinking about the project, and this is the AI class. So in general, I strongly encourage you to use AI tools to do your project. But when you present or write paper, you should do it in your own language. You should interpret what AI gives you, and if I read it, it should sound like you wrote it. You should not sound like AI. You just dumped everything to AI. Okay. So I don't care if you use AI or okay. I actually encourage you to use AI, but I never said that. Okay. I never said that in officially. Okay. And when I read your project report or your presentation, I don't want to look at AI prompts. Okay. I want you to post-process it so it looks like you didn't use AI, okay? You should present it in your own language. But unofficially, I strongly encourage you to use AI as much as possible, okay? But you cannot just, do screen capture of ChatGPT and give it to me, okay? You should interpret and post-process the output. Okay, so this is going to be walking you through PyTorch. So we've done lots of custom things, creating matrices, and we created our own optimizer for Atom, RMS proc, etc., and did lots of reshaping and everything. But from here and there, we already use some PyTorch functions. So it's a Python library that supports pretty much everything you need: automatic differentiation, neural network models, optimizer, and training and inference code, loading the data, feeding it to your CPU, GPU. Everything's taken care of. So you must do a self-study for your project, but it's easy. And syntax is pretty much the same as Python or NumPy. So here, we're going to walk you through some useful tools. And the first thing is you need to have access and control how you use your GPUs. So for the project, we're going to give you, each team is going to receive one instance of L40 GPUs. And how do you check the status of a GPU? You can do, in Linux, this exclamation mark is if you want to execute some command from Python. So from Python, if you do exclamation mark some Linux command, you can look at the output in Python. So in Linux, you can just type this much, NVIDIA-SMI. It gives you status about your GPU. So it gives you lots of useful information like the temperature and the name of the GPU. And the most important thing you need to look at is this line here. That's the memory usage. So throughout your project, you're going to see lots of instances of OOM error from GPU. OOM stands for out of memory. So for this instance specifically, we have 15 gigabytes of memory available in GPU. That's total, and this is how much we're using right now. So when this number, it's getting close to this number, you need to do something else. Decrease the model size, or change how you're going to use your data. Don't feed too much data here, right? So the easiest thing is to do one. So let's say you're doing fine tuning and you get out of memory error. And what's the easiest thing to do? Right, exactly. Change the batch size. It linearly is going to bring down memory usage. Okay, so you're going to see this. You're going to look at this screen, I don't know, like 10,000 times during the project. So this is very useful command. And if you have multiple GPUs available in your machine, this is going to be the GPU ID. ID 0, ID 1, ID 2, etc. Okay, so let's connect. Okay, I actually encourage you to use coding assistant tools like Cloud Code or Codex. So if you're only using ChatGPT, this is a time where you need to jump outside your comfort zone, and you need to use Cloud Code or Codex. It runs in console and automatically adjust your code. You can even ask it to execute the code. And the important thing is if you give it some tools so that it can check for itself the validity or the correctness of the output, that's when you get 10x or 100 times productivity increase. If you just use it iteratively, then it's going to be active only when you're awake. Right? If you give it tools so that you can verify the output, you can keep running even though you're sleeping or having lunch or going out on a movie date or whatever. Okay, that's the important thing. So some companies are. So when you train a model, you typically use what's called weight and biases. It gives you the training curve and loss curve. Basically, whatever it outputs during training or inference, it gives you a log of training loss, test loss, or some metric or whatever. And what companies are doing is it exports whatever's in the weights and biases to the AI. And AI checks how well it's training or how well it's performing automatically without you in the loop. And based on what AI thinks, based on the summary, it tries to change the training code or some inference code. And then once you complete the loop, you don't need to interfere, so your productivity increases. So at minimum, you should see 3x improvement because it's gonna, work continuously. Okay, so PyTorch. So this neural network module already gives you various building blocks that you already need. So what you need to do is import Torch and import neural network module, and if you can create tensor from PyTorch using randn, and this is going to be the linear layer of size, input dimension, output dimension, And if you do linear parentheses x, it's going to give you matrix multiply output. So yeah, input size was 2 by 64. We did matrix multiply with matrix size 64 by 256. Output is 2 by 256. And activation functions, there are two ways to do it. You can do it through the module API. So neural network, we imported it as nn.relu has everything. Every nonlinearity is available. Or you can use what's called a functional API. From the NN, you can import functional. You can do f.relu. They're exactly the same. So I want you to just look at what's inside the neural network module. Do a Google search here, or just look at it from the official documentation. So how do you build, for example, 3-layer MLP with SNU activation? So we're going to subclass or derive from NN module and call it class MLP. And we're going to call the super initializer and create these weights, W1, W2, W3, with nn.linear, and activation function we're going to call nn.SNU. So chances are, if you're implementing something that is not PyTorch, you're doing something wrong, because pretty much everything is already implemented. Okay, and this is forward, and you have your input x, matrix multiply first weight, activation, second weight, activation, final weight. In case this seems new to you in class, in Python language, this calls the initializer of your whatever you are deriving from, your superclass. Calls the initial constructor of this class. Okay, so let's test our 3-layer MLP. So compare this to our previous implementation. This used to be in and of itself like 10 lines of code, and this used to be, I don't know, like 5 lines of code, everything. Okay, so we created some random tensor, and we pushed the first input, and let's check the shape of the input and output. Input shape is 2 by 32. Output shape is whatever the final dimension is. It's same as input dimension, so we should expect the same dimensions. And this is the computed output for 3-layer MLP with SNU activation. You can also recognize gradient function atom backward by default. How do you save and load model weights? So this is going to be very useful to you, because if you turn out to do fine-tuning, it's very, very important that you occasionally save your model weights. And in case where your machine crashes or your instance crashes, you don't start from scratch. You load whatever is stored in the latest memory. So this is very important if you want to preserve your progress. Okay, so very, very important. So how do you get the weights? This is your class object. You do state underscore dict. This is going to be give you the weight object. And it's going to be a form dictionary, and you can see what's inside. Anyways, if you want to save it, do torch.save weights and your file name. And let's say your machine crashed. How do you load your weights? Then you do torch.load file name, and then you first need to instantiate empty model, and from the empty model call load state dict with the weights, and this is going to overwrite your randomly initialized weight with whatever is saved in this file. It's going to be also important because you need to submit the saved checkpoint. Okay, so just to make sure, let's create some matrix, some MLP model, save the weight, reinitialize, load the saved model, and see if the weights are pretty much the same. So we passed the assertion, and this is what's stored in the keys. So I said it's a dictionary, so we're printing the key and values for the dictionary. So what are the keys? All the layer weights and biases are the PyTorch tensor. And why 3? Because we created a 3-layer MLP here. Okay. How about the optimization? So for AutoDiff, how do you compute the gradient? So create a tensor called backward function and saved at tensor's .grad variable. So let's create some function that takes that computes L2 norm squared, and the gradient is going to be 2 times x, right? So let's verify it. So we're going to create some random tensor, and default is required grad is equals false. If you set this equal to true, then it tells PyTorch that you want to backprop to this tensor. So this is your loss function. You do L1y squared and sum, or compute L2 norm squared, and from this output, leave tensor in the computation graph or the loss computation node. You compute dot backward, and let's check if it correctly computed the gradient. So this is the leaf tensor 16.5. That's your loss function. And from x, we're going to call .grad variable to check whether the correct gradient is stored in the x, and check it against 2 times x to verify it against the numerical analytic gradient. So all closed output is true. So up to numerical precision, the output is correctly computed. So important thing is when you create a tensor, so all the weights need required grad equals true, and from the final leaf node in the computation graph or the loss node, you need to call dot backward. Unfortunately, we're out of time. So rest of the stuff, optimizer and training code, example training, GPU to CPU, memory moving, and Hugging Face, we're going to cover it next time. Thank you.